Hi, Tai-Danae. I'm very happy to be back with you on fAQ today to talk a little bit more about what's actually going on inside a trapped ion quantum computer.
Yeah. Hey, Adam, this is going to be a good one.
I think it is going to be a good one. I'm extra excited about this one because I think I'm actually going to learn a lot from you, and not to put no pressure, not to put anything on you there, but I'm excited to really pick up some stuff here from you, especially when it comes to the math of quantum computing. Very excited about that. But before we even get into that, I want to do a quick little recap about how this conversation has been going.
Yeah.
So the whole point of all of this is to really dig down a little bit deeper into what's actually happening inside a quantum computer, in this case, a trapped ion quantum computer. Get, a little bit deeper than just the theory and really try to develop a good intuition for what's happening actually inside some of the hardware.
Yes.
And we're doing that using a framework from DiVincenzo's criteria, which essentially I think of as a checklist of all the things that you need to have in order to have a fully functional quantum computer. And we've been kind of going through those different criteria in each one of these conversations. And we've covered the first two. The first criteria was a scalable physical system with well-characterized qubits. So we had a conversation about that. And then our last conversation was around qubit initialization, or in other words, the ability to initialize the state of the qubits to a simple fiducial state. And we've had those conversations and they're recorded. I know I'm going to be going back and probably checking on those every once in a while. So nice to have those kind of in our list of these podcast episodes. And today we're going to be going a little bit out of order. We're going to skip DiVincenzo's criteria number 3 and go right to 4, which is a universal set of quantum gates. And we'll come back to number 3 later. But we're going to start off with this one talking about quantum gates. So the first thing that I think we should probably get into is this concept of a gate. Like, what is a quantum gate? And I can say that when I first heard about gates and first was hearing about qubits and quantum computers, in my mind, what I sort of was thinking of is this like blob of the qubit. I'm a little bit better now about what a qubit actually is, but at the time I was just kind of thinking of this like glowing orb and it passing through kind of like an arch, like an archway. And like it's in one kind of configuration before it goes in that archway, and then it passes through that archway, and all of a sudden now it's like something else. Nobody told me to think about it that way, but that's kind of what I was thinking about with quantum gates. And I think that from our previous discussions, I'm starting to learn a little bit more about what's actually happening when you talk about a gate. And we talked last time about how to initialize qubits and how we can essentially shoot lasers at qubits and manipulate their energy level and sort of transform the state or the energy state or even the vibrational state of a qubit. And my understanding, I definitely want you to check me on this, but my understanding is that the shooting of the laser in that case, or the transformation of energy of the qubit, that is the gate. So the gate is like giving energy in some way, shape, or form to the qubit in order to change its state or transform it. Does that resonate?
Yes.
To use that word, does that resonate with you?
But it does resonate with me. And in fact, I think your analogy is not too far off. Like, you have this qubit and you're thinking of it as like approaching some archway, and then it passes like brand new somehow. I guess the only modification would be, rather than the qubit going to some archway, it's like the archway is coming to the qubit. Like, the archway is the laser and the qubit is standing in place, and your laser is coming and it's affecting it in some way. And then that transformation from, my qubit was in this state, then, through this transfer of energy via this laser, it's now in this other state. That whole process is called a gate. So I think it's exactly what you said. And the analogy is just like a weird one where the gate comes to you rather than you passing through the gate.
Yeah, I don't know where that came from. Like even just the word gate.
The wording?
It feels strange to me, but it's all coming together now. Like that maybe some of this cuts to like quantum circuits and things that we'll get later, and kind of how all those are like laid out. But yeah, it does kind of feel like the qubit passing through a gate, but you're right. Like, it's really, you're bringing the gate to the qubit. And in this case, like the laser is the effector of the gate.
Exactly. Okay, so I think that's a good high level understanding of gates. We will get to that in more detail in a little bit. But maybe we should also talk about this other word, universal.
Yeah.
Universal set of gates. So I don't know. Do you have any? I have an idea, but maybe you want to say something.
I mean, yeah, I think I'll be very brief on it. And just my initial gut reaction to universal, to me, just means that we need a set of these gates or these transformational powers that when they come together, when they're combined, they can perform any mathematical calculation. That's kind of my from the hip interpretation of that. What do you think?
No, I think that's right. And the interesting thing, though, is that there's a theorem. So any like operation you want to do, and I should say reversible, like we have to be like if we shoot the lasers and change the qubit from one state to another, you should be able to like hit the rewind button and undo that. That's like a constraint that you want in quantum computing. So any kind of reversible function that you would like to do on your qubits, let's say you have, a bunch of them, like 10 in a row, and say you want to transform all 10 at a time. It turns out, it's a theorem, that you can do that by operating on one or two of them at most at a time. So like anything you want to do on the collection of all of your qubits, you can implement that thing by only hitting lasers on either individual qubits at a time or two of them at a time in some kind of sequence, almost like playing notes on your keyboard, and you can play this beautiful melody by only pushing one key at a time or two keys at a time. You can basically get any song in that way. That's kind of a lame analogy, but that turns out to be a mathematical theorem. But the reason that I mentioned that is because today I think we want to talk about what is a gate on a single qubit, and then maybe next time in the next episode, to avoid this conversation going on too long, we're going to cut it in two. And next time we'll talk about gates on 2 qubits at a time. And so the reason that people like to talk about 1 and 2 qubit gates is because of this theorem. Like anything you want to do on like 100 qubits, you can implement that by only operating on 1 and 2 at a time. So it's like simple. It's like building a nice construction out of little Lego pieces or something.
Gotcha. So, I mean, kind of sounds like that you're building up a complex toolkit from simple tools.
Yes.
Is that okay?
Yes. Thank you for summarizing it nicely.
No, exactly. You're dropping the knowledge. I'm telling you, I'm learning a lot already with this one. So, no, that sounds great. Thanks.
Yeah. All right. So maybe if now is a good time, we can park for a little bit on like a 1 qubit gate. What does it mean to have a qubit in this initialized state that we talked about last time? That's like that 0 state, the last time we talked about like the quantum version of a 0, which mathematically is like a 0 with a vertical line in this right angled bracket, or ket 0. So we talked about what that means actually last time. How do you put a calcium ion specifically in this ground state, this lowest energy state? We talked about that last time. But now a 1 qubit gate says, oh, you should be able to change the state of that qubit, that calcium ion, into some kind of, okay, I'm going to use this word now, superposition of the ground state and the excited state, that lower energy level and the higher energy level, by laser somehow. That's called a superposition. We've talked about that before in season 1 of fAQ, but now we actually want to say, what does that mean concretely? So what do you think? Is now a good time? Should we review a little bit about energy levels of calcium ions, or should we just assume people remember that?
I think maybe just like a little bit of review from that initialization conversation that we had. We just talked about, the ground state and the excited state, and we could shoot some lasers and move the energy level of that valence electron, that electron in the outer shell that's really modeling the qubit. The energy level of that electron is modeling the qubit, or is the qubit. And we talked about how we can manipulate that basically from a 0 to 1 and even kind of back to the 0 level. Yes. But the elephant in the room there was that's just bits. That's just zeros and ones, yes, which we already kind of know about from classical computers. And I'm excited to talk about like some of the extra power that you can get in quantum computers, which is that superposition piece. So I think that feels good to me. But if there's more that you want to jump in there with the energy levels, let's go for it.
No, that was perfect. That's a good recap. So let's pick up from there. I want to focus on this word superposition for a while and kind of slowly unwind it. So what I would like to do in order to understand the word superposition, we do need to like look at the math a little bit, but like if like listeners, don't be scared. It won't be too bad. And then we're going to tie it.
I'm a little scared.
Don't be scared. Don't be scared. It's going to be fun. Okay. It's going to be fun.
All right. I trust you.
Okay. So here's the thing. Usually, Adam, right? When people in, popular media or pop sci articles or videos or whatever talk about superposition, you and I have discussed it before. Usually it's explained as, the ion is both in the ground state and the excited state at the same time, right? There's this language at the same time. Or it's both a 0 and a 1 at the same time, and you're laughing because we're like, that's terrible. It's terrible. Okay. I hope by the end of this episode that everyone listening will agree that that is not good language. I'm going to be really honest with you. As I was preparing for this discussion, I was really baffled about, why does that even make sense? It does not make sense, and that is absolutely not what superposition is saying. I'm not sure where that shorthand language came from, but I'm kind of even more frustrated now after having given some thought to it. So I'm gonna convince people why I feel this way.
Great.
So let's talk about superposition. And I'm going to say what it really means, and then maybe looking back, we can kind of, see, does the both at the same time language capture that, and then what's really going on in the laboratory with our trapped ion quantum computer, okay? But just by way of refresher, here, Adam, I have a picture of an ion. This is not a real picture. I just scribbled it on my iPad. But what we were just saying is that at the end of the day, there's kind of two things your ion could be doing. Either it's in its ground state, that lower energy level that you were just describing, or it's in its excited state. What do I mean, it's in those states? What I mean is when you go to measure your ion, and now, unfortunately, we kind of have to let the cat out of the bag for DiVincenzo's criterion number 5, which talks about measurement. So I have to say this, but I want to help this topic feel less spooky. But what we mean is when you go to probe your ion, i.e. when you shine a laser on it, you might find, if you set everything up correctly, that either your ion will kind of glow a little bit or it won't glow. And we'll talk about that in another episode, exactly how do you know that? But either your ion will kind of fluoresce or it will not fluoresce. And that's how you as the person know what state your ion is in. Let's say if it's in the ground state, if you set everything up correctly, you shine a particular laser with a particular frequency on it, and then you see a little glow, that tells you, the observer, my ion was actually in its lower energy state. Or if you shine that laser and you do not see a glow, you say, it was in its excited state. Okay, so that's kind of how you translate from quantum physics to real people, macroscopic world. So those are the two options that you can get. But it turns out that for reasons that belong to quantum mechanics, you can't really say definitively prior to doing this measurement or prior to shining this laser, definitively whether you're going to get fluorescent glow or not. But you can know that answer with a certain probability. Okay, so why is that? Just, I don't know, ask the laws of nature. That's how it works at the quantum mechanical level. So there are certain probabilities attached to it. So those probabilities are where this idea of superposition comes in. So in other words, you can think of each state, the ground state, or the excited state, as being as having a number associated to it. So I'm just going to call the number associated to the ground state, this kind of glowing option, let's call that number A. I mean, A is a letter, but I'm not specifying what the number is, so let's just call it A. Okay. And then let's call the number associated to the excited state, the not glowing option, B. Okay. These aren't quite the probabilities because you have to do an extra step. So it turns out, for very nice mathematical reasons, but we can kind of just take our word for it now. that if you take the number A associated to the ground state and you square it, that square is the probability of finding your ion in the ground state. Okay, so it's the number, but you actually have to do this extra step of squaring it to get the probability. And same thing, I can have, my ion set up with probability B squared. I'm going to, when I shine my laser and do this measurement, with that probability, I'll find it in the excited state. So that's as much as you can say in quantum mechanics. I have these two numbers, and if I square them, I get the probabilities that I'm going to, either see the ion fluoresce or not see it fluoresce. So, if A squared is like 0.5 and B squared is like 0.5, that means if I have my ion and I shine a laser 100 times, 50 out of the 100 times I'll see a glow, and 50 of the 100 times I won't see a glow. That's kind of what those numbers mean. Okay?
Okay.
Is this okay so far?
I think I'm following. Like, I'm not sure where you get the original A and B number from, but I'm guessing you're going to get into that.
Okay. Yes. Everyone, Adam just said, where does the A and B come from? Adam, that is the climax of this entire conversation. So take that question and put it in the back pocket somewhere. Okay. That is exactly where we're headed.
Great. If it's not clear, I don't know what you're about to be talking about. So
yes,
we don't have these conversations ahead of time. So if I let anything out of the bag, just let me know.
It's okay. This is great. Okay. I love where you're going. So I want to, before we get there, I just want to say, everything I just said is a mouthful. I've been talking for 2 minutes already? It's too much, okay? So to put that whole scenario in succinct words, people say succinctly this whole package deal, one simply says your ion is in a superposition of its ground and excited states. So that whole scenario about with this number and you square it and you get this probability, blah, blah, blah. Instead of saying all of those words, which is 153 words, I didn't count. All of that is just succinctly summarized by saying, oh, my calcium ion is in a superposition of ground and excited. And you can be more specific, it's in a superposition with these numbers. Where do the numbers come from? We will get there. But let's just say someone has given us some numbers and that's the scenario. That's what superposition is. It's describing that setup.
So it's describing the probability that you'll find the ion in one of those states?
Yes. All right. That's exactly right. Now, the English language is good. However, sometimes it can be a little cumbersome. For example, that's a lot of virtual ink. Right? So you can also express this mathematically. So that English sentence, the ion is in a superposition of its ground and excited states, translates from English to mathematics by this expression. So what we have done is, it's like a name tag. This ket 0 is representing the ground state. Instead of writing the words ground state, we just write a 0 with these funny parentheses next to it. And you can imagine a sticker, the letter A, the number A is just a sticker, like the hello, my name is sticker. So you have your ground state and you slap on this A sticker and it's just reminding you, oh yeah, that's the number associated with the probability of that state. And then you do the same thing for the excited state. Excited state, we also sometimes call it 1 with this funny parentheses. And so you just slap that B number on that state. It's just kind of like a labeling. Okay, and then people write a plus sign because it turns out that if you associate mathematical meaning to these symbols, you can actually add them in very concrete ways, but that's another story for another day. That's linear algebra. But you just imagine, I have two states and they each have numbers associated to them. So I will just write those states down symbolically and write the numbers next to them. So that's the mathematical way of writing this superposition. So you can have your pick. You have English or you have math.
Okay.
How's that so far?
No, I'm following you.
Okay.
But one question that I have, and just tell me if you want to talk about this later, but
yes.
like those A and B name tags
yes.
have to like be related in some way, right? Because
yes.
Okay.
Yes.
Okay.
So A and B, like in principle, could be arbitrary. because maybe you're doing some theoretical calculation or whatever, or maybe they don't matter at the time. But yes, in a trapped ion quantum computer, they absolutely are related to one another, and they're related to the whole setup that you have. Like they're related to the laser, and they're related to how long you're shooting the laser, and they're related to the ion and all of that. Absolutely. We're getting there. This is like the next question after your first question. So I love where you're going. But I'm taking the slow route, because if we were to just jump into that hardcore stuff, I think it'd be massively confusing. So I kind of want to connect this to what things people may have seen before, which is this funny notation.
No, that makes sense to me. And again, we can push this, but if we're talking about probabilities here and you're adding them together,
yes,
like one way that they're related is that they have to like be added up to equal 100%, right? Like, so you talked before.
Yes. It's not that A and B equal 100%, but it's A squared and B squared equal 100%. And I should have said this earlier. There's like all these caveats. It's not technically A squared, because A could be a number that we're all familiar with, but there's these other kinds of numbers called complex numbers, which you may have heard of before. So to square a complex number, you have to do like a little twist. So I'm kind of sweeping that under the rug, but you basically just think of squaring, like multiplying a number by itself. Yeah. Okay. So exactly right. They're related to each other because A squared in quotation marks plus B squared equals 1. So that's absolutely a constraint you must have. The reason that they have to add up to 1 is that your ion is doing something. Okay? And if you only have two options, I mean, either it's doing this or that, and that's all that there is. Like either it's ground or excited, and that's all that there is. So yeah, when you go to measure it, you're going to get one of those two options with certain probabilities. But the thing is, I think the interesting thing is, okay, but what's it doing before you measure it? What's it doing before you shine the laser and either saw a glow or not? And I think like we're not allowed to ask that question, or I think if you do ask that question, then things get confusing. And I think maybe that's where the both at the same time comes in. It's like, well, we don't know, but maybe one way that we can explain it is like it's both at the same time until you shined. You hit the laser with it. And I'm not sure if that's the best explanation, I mean, I think that's confusing, but I think that's where the language comes from. It's like, okay, that's what it's doing after, but what about before? Mm-hmm. Well, we're not sure. It's very murky. So both at the same time, question mark?
Yeah, that might be just conceptually easier for regular people that don't like have this mathematical background. It might be easier for them to kind of imagine that it's like both at the same time instead of imagining some mathematical formulas that you're going through. But I like how you're going through them. They're not. It doesn't. So far, so good. It doesn't seem all that complicated so far.
I'm so glad. Okay, so we haven't ruined your math experience yet. That's good. So let's keep going. Great. One thing I want to say that's kind of a tangent, not really important, but sometimes people by people I mean physicists, like to give like a nickname to this expression, and it's called psi, the Greek letter psi with this funny angled bracket. So I'm just saying like 2 plus 3 is 5, and instead of saying 2 plus 3 in all of our conversations, we just say 5. So instead of saying A0 plus B1, we just say psi. So I'm just mentioning that because basically in every quantum physics text, you'll see this letter psi with the bracket, and that's like the letter of choice for this sum.
Okay.
So just that'll come up later. All right, but let's get back to what you said, okay? I like what you said. Maybe this language of both at the same time is just kind of used for like non-technical reasons about describing what's going on before you measured your ion, and maybe that's confusing, but if you actually look at the math, it's like way more concrete than that and not as spooky and esoteric and weird. So to reaffirm that point even more, Adam, I would like to show you a picture of superposition, okay?
Okay.
A picture of superposition. Do I have permission to show you this picture?
Please, encouragement, yes.
Okay, fantastic. So drum roll, please. Okay. Here's a picture of superposition.
I think we might need a
Now,
little more
you may
explanation
say, wow,
here.
this is so underwhelming. It's just like a plot of some curvy lines. So let me explain, first of all, where this picture has come from. So this is a graph that folks can find in a Penny Lane article on trapped ion computing. You and I have referenced this article on this podcast before. I think it's fantastic. It's really well written. And it has lots of nice, fun GIFs and pictures, which I just think are great. So I really enjoyed reading this article, and so this graph is from there. So let me kind of explain what this graph is showing and how this relates to the whole conversation. So it turns out that the probability, let's say, of finding your little calcium ion in the excited state, meaning the state where you shine a laser and you don't see it glow, you don't see the ion glow, that one. The probability of finding your ion in that state depends on a number of things, including how long you shined your laser for. Was it like beep, or was it like beep? Okay, so it depends on the length, the duration of the laser pulse. And it also depends on some other factors like, physicsy things like, the magnetic field associated to the laser and this like dipole moment of the ion and all of this technical stuff. But you can imagine it depends on like the context that you're in, the physics that you're in. So this is a graph. If you look on the horizontal axis is time and the vertical axis is probability. And it says, the units of time are in, okay, it's got this symbol. Let's not worry about it for now, but like each vertical tick mark, or they're in units of 2, but like this, these are in units of 1/100,000th of a second. So this is like very small, okay? So this first vertical line is 2/100,000ths of a second, and so on. 2, 4, 6, 8, 10, 12. So this says, as time goes on, the probability of finding that your ion is in the excited state is given by, you just go on the x-axis and then look and see where your finger kind of hits it and then look at that probability. So the probability fluctuates over time. This is a picture of superposition because, for example, let's look at probability 0.5. That's 50% probability that my ion is in the ground state or the excited state. Like 50-50, it shines or it doesn't shine. So how long do I have to shine my laser for? Well, if I follow the graph there, it's like, what is that, 1.8 units of time, maybe-ish? I don't know. It's like a little less than 2. So that 50-50 is exactly that superposition that we're talking about. That's like, this is the quantum version of flipping a coin. Like, oh, it's heads or tails 50% of the time. Well, this says you'll find your ion in the ground or excited state 50% of the time if you shine your laser for this long. But you can get any other probability on this graph too just by adjusting your time. This is what superposition means.
Okay. It's like, when I'm first looking at this, kind of blows my mind that it's just like what we were talking about before in the last conversation around gap energy lasers and things like that, except at like a finer scale. So like if you're just controlling the amount of time that you're shining the laser on the ion, and that is like ratcheting up the probability that it's in either the excited state or the ground state. Is that correct?
Yes.
That's
exactly. That's it.
That feels, I know that you said there's some other complicated stuff going on there, but that feels pretty straightforward and concrete.
Absolutely. Good. I'm so glad. So it's like, where's the mystery?
Okay. So I have a question and a comment. So I'll start with the question. So superposition doesn't just mean the quantum version of a coin flip of 50-50. It's any of these probabilities between 0 and 1. So like it's still superposition if it's 0.25 on one side and 0.75 on the other side. Yes.
Anyone, any of those, any two numbers such that you square them and they add to 1, that's called a superposition. It's interesting though. I don't think you were asking this, but I must say it. it's interesting that you were like, oh, but what about coin flips? Like, I have an unfair coin that's got probabilities 0.25 and 0.75. Why don't I call that a superposition? Like, I didn't learn that in middle school. Okay, here's the thing. Technically, you could do that. Okay, so as you saw, this whole superposition discussion about the A's and B's and zeros and ones had nothing to do with like quantum physics, the laws of nature, nothing. It's just a word that I gave to a mathematical expression. Mm-hmm. That's really the beginning of linear algebra. So what you have just uncovered is the fact that this concept is very simple. And in the world of mathematics, like you can do stuff with it, and it can apply to coin flips. It can apply to like, I don't know, anything else that you want to add with numbers that add up to 1, like fine. It just happens to be that in the world of quantum physics, because there's this physical interpretation attached to it, that notion is called superposition, even though the actual mathematical concept can be applied to like anything. But I think when people say superposition, implied in that is we're actually talking about quantum objects, even though this broader concept can be applied to non-quantum-y things.
Yeah, that actually brings me back to our season 1 episode on superposition and talking about like geology and things like that.
Exactly.
Okay.
Yeah, people should go listen to that. Okay, but that was your
yeah, that was the question.
Comment. I think you had a question.
No, that was the question. Okay. Yeah, my comment is that looking at this curve and looking at the incredibly small amounts of time, especially on these like steep parts of the curve, that makes me think about when we were talking about the difficulties in scaling quantum computers, how we talked about that, control over lasers is really important. I think I might have even said that without really knowing what I was talking about. But now when I see this curve, like, oh my gosh, if you want to make sure that you're getting like a 0.5 probability, your laser better be really tightly controlled, because if we're talking about a hundredth of a second, if you're off by 100,000th of a second, all of a sudden you're in a much different place than where you wanted to be. So this kind of really brings it home for me that the challenge of laser control, timing, intensity, like making sure that you have the wavelength of that laser exactly right, have it aimed in the right spot, and have it turn on and turn off at the exact right time to the fidelity of like these tiny time periods. That really like brings it home to me about the challenge of laser control.
Yeah, so same here, and I'm glad you mentioned that, because I also feel after having spent time with this material for this podcast, I feel a very deeper appreciation for the engineering behind all of this setup. Like, I think it's really amazing. Not only can people understand the mathematics so clearly, and we're going to get to that in a second actually, but that you can also implement those things in a lab, like with these finely tuned equipment. I mean, it's really impressive, really, really impressive. I do not think I appreciated that, as like an undergrad in college or something.
I don't think I appreciated it like 5 months ago. So. Yeah.
Okay, same. All right. So now that we have seen a graph of superposition, and I'm so happy, I think our takeaway is it's not as inaccessible of a concept as one may be led to believe by just like reading stuff on the internet. But now I want to get to your original question that we said put in your back pocket. So let's take it out of the back pocket and answer, okay, but where did this graph actually come from? Like, I said this is a graph of superposition. I did get it from an article written by, like people with authority who know what they're doing. But let's understand where they got this from. And to understand that, I want to revisit your question earlier, which is, where do you actually get these numbers A and B? Like, where do you find the A and B such that if you square them, you get 0.2 and 0.8 or 0.5 and 0.5? Mm-hmm. I was kind of hinting that comes from kind of the physical context. So now I want to say that. So remember, the whole state, the whole superposition, sometimes we like to write it as psi. So psi is some number, labeled with the ground state plus some number labeled with the excited state. So A and B. Okay, here are the numbers. Ready? Drum roll, please. Okay, there they are.
Okay.
Well, this looks a little bit scary because the first number turns out to be the cosine of something. So now we have to think back to trigonometry. So it turns out actually that these numbers are defined in terms of trig functions. I hope this is not bringing back nightmares from, when did we learn trigonometry?
High school, maybe? Yeah.
High school? I don't know. That was like centuries ago. Okay, but just think of like two trig functions. One is called cosine and one is called sine. If people do not remember that, here's the thing. If you pull out your iPhone or whatever smartphone, or even your like TI-83 calculator, there will be a button that says COS. So all you have to do is punch in a number and then hit that button and you get another number. So that's what I mean by cosine. You don't even have to know what this function is. It's just like a button you push on your calculator, given some number, and it spits out another number. Okay, so that's what cosine is. So I have written here, cosine of something, cosine of some number. I don't want to tell you what that is yet, but you get a number, and that's the A. Okay, now here's the other number B in red here. Well, you can see there's like sine of something. So that's another button on your calculator. But then you also have this exponential. So now we kind of have to remember, oh yeah, back in high school, I did learn that there's this other function called e. And if I take e and raise it to some number, that's also a button on my calculator, so we don't have to think too hard, I get another number. So that's what they mean here, or that's what I mean here. Okay, so there's a sine, and you multiply that by e of something. These are just numbers. But then, okay, this is the last bit. You see this letter I here? The letter I, you should think of it as the number such that when you multiply it by itself, you get -1.
Okay.
Now, that should cause you to pause what you have done, because if you think about this, if I multiply any number by itself, it has to be positive. Like 2 times 2 is 4, that's positive. 3 times 3 is 9, that's positive. 0 times 0, well, okay, 0, so it has to be non-zero, non-negative. What's -1 times -1?
1.
+1, yeah. -2 times -2 is +4. So you cannot take any number that we know of on this planet and multiply it by itself to get a negative number, much less -1. Except you can. We just define the letter I to be that thing that doesn't exist that we wish does exist. So this is the beginning of complex numbers. So I is like a placeholder, or a new symbol, and it represents this imaginary thing, this imaginary number, such that when you multiply it by itself, you get -1. So numbers now that have I associated with them, this whole new number system, these are called imaginary numbers or complex numbers. It sounds like total loony bin stuff, but it turns out to be fundamental to science, including quantum physics. So I would just say, if this is the first time folks are hearing of this thing called I, don't worry about all of the implications. It's very interesting and you should go read about it. But for, a first pass, just think of it as, I is this letter such that when I see I times I put an equal sign -1. That's kind of what it is referring to. But it turns out to be useful here. So when you multiply I times sine times e of this thing, you just get a number. And when you when you take cosine of something, you just get a number. And these are like the A's and B's that we were talking about earlier. But I'm trying to convince you, how do we know this? How do we know this? And what are the somethings? So that's the next layer. So I'm just going to show that to you now. It's going to look a little bit messy. And then we can close all of this by saying, how in the world did people know this? Why is there an I there? Where did this cosine and sine? Who is making life difficult by using this stuff?
Great.
Okay, so to answer that question, I have to make it more difficult. So here are the somethings, okay? So it's some stuff. There's an omega, which is the substitute for some number. There's the letter T, which is just the substitute for time. That's how long you're shooting your laser, and then you multiply those and divide by 2. Now this omega, it doesn't really matter, but it's something called a Rabi frequency, which is relating to this kind of internal state of of your ion. So you can imagine there's things you're interested in, like the magnetic field associated to the laser that's shining to it, and like this dipole moment of blah, blah, physics stuff. So this omega is a number, and it's related to the physics stuff. T is time, how long you're shooting your laser. Over here, you see e to the I phi. This is just a number. This Greek sign phi, this is relating to the initial displacement of your laser to the atom's position. So I think that's like, here's my laser, it looks like a wave. Like, at what angle is it hitting my ion? Is it like this? Is it coming like this? Is it like head on? So you're interested in that as well. So I think that's what the phi is referring to. So you can imagine there's like stuff going on, and they have certain quantities, and you just want to like plug those in somewhere. So that's what all of these symbols mean. The punchline is, these are numbers. They're kind of like variables, and you can plug them in. And here's like the upshot of all of this. This is just what we said before. The probability of measuring your ion in the excited state is the square of the red number. It's the square of this B, which is like this whole shebang, like I sine blah, blah, e to the blah, blah. But the point is, you can plug in numbers for those letters, and you can get a number that you can plug on your calculator. And so what you're seeing in the graph is just a plot of the absolute value squared of that term sitting, that term that's labeling the excited state. And when you do that and you work out all of the mathematics, and I think you can plug in a certain number for this omega, that Rabi frequency, it's like, according to the Penny Lane article, I thought this was helpful. They say a typical number that you can plug in is 100,000 hertz. You get a number here. And you can plot your sine squared function, just the square of that term, with respect to time. So you don't plug in time, you let time vary. And that's exactly the graph that we were seeing before. It's what we said at the beginning. You just have a number. In this case, it's very specific to the environment, the context of your setup. But it turns out to use this trigonometric function sine. And when you plot the square of that, you get, this is exactly the graph of the sine squared function with respect to time. That was kind of a lot, but in this case, the A and B, those numbers, the 0.2 and the 0.8, they come from these very complicated equations. But the reason for like reverse engineering this conversation is so that you can see, even though it looks complicated, when you plug numbers in, you get things like 0.2 and 0.8, or 0.5 and 0.5. So it like all collapses to very simple arithmetic, essentially. How are you feeling? Is this is this terrible? Do you want to leave this conversation? Should we stop the podcast? What do you think?
No, I never want to leave these conversations. I think I'm getting it. Some of the math is a little like high for me, or for what I'm kind of used to, but I like being able to bring it back to like the practicality of like that math. You can dig into it and learn more about kind of where the numbers come from, but you can also then practically, because we always talk about like what's actually happening in practical applied terms, you can use those numbers to then generate like this graph that we've been looking at, and then that graph is the theory and the practicality or application coming together, and you can use that along with the formulas that you've been showing to actually like figure out what you're going to do inside your trapped ion quantum computer to get those qubits manipulated in the ways that you need to in order to do a calculation. So it's all kind of starting to come together for me a little bit. Okay, great. So maybe I can say one thing, which is to hint back at your question. I still really haven't answered your question, which is, where did all of that come from? Like, why cosine, sine, exponential? Why all of this crazy mess, right? Like, why? How did we know that? How did the Penny Lane article know that? Okay. I think a nice way to explain this is by forgetting quantum physics for a second. Do you remember back in like the first time any of us ever learned physics, there's these things called Newton's laws of motion, that basically explain like how planets move and why like I roll a ball down the hill, like we can predict things. So essentially, if I have like a ball or some object and I'm interested in its motion, given some forces that are acting on it,
If I can tell you its current position and its current velocity, and then factor in all of the external forces, then I can analyze these things called Newton's laws of motion, and I can tell you what it's going to be doing 5 seconds from now. Right. So this is like flashback to physics 101 from college freshman year, or I don't know. I delayed physics actually till like my junior year in college because I was a little scared of it, but now I love it. So aside. Okay, well, it turns out that there is an analog to Newton's laws of motion in quantum physics. So if I have a quantum particle, like an ion, and I know kind of what it's doing, then there is a law or an equation that says, great, if you tell me what it's doing now, and you can tell me the context that's around it, I can tell you what it's doing, like t seconds from now, like 1/100th seconds from now, 1/100,000th seconds from now. Okay? Instead of calling that Newton's laws of motion, the analogous thing is called Schrodinger's equation. Schrodinger's equation. So Schrodinger's equation looks like this. It doesn't really matter. But the point is, there's that psi. There's that state. That psi is the whole cosine, sine, blah, blah stuff, okay? And it comes from this. And Schrodinger's equation basically says, if you tell me the context, the physical context, what's like around in the environment of my ion, then I can tell you what the state of the ion is going to be in a certain time from now. So this equation is kind of telling you how it's evolving over time. Let's forget everything, but let's not worry about anything. But let me just point out this one thing, this letter H. That's like the bucket where you dump in all of the information. Like that's the bucket where you input all of the strength of the magnetic field and this Rabi frequency and blah, 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 all of this stuff and the phase of like you dump it all in there. Concretely, it's this thing called a matrix, which is like an Excel spreadsheet of numbers. So you can imagine you go into your Excel spreadsheet called Schrodinger's equation and you like insert all of the relevant numbers, the omega and the t and the phi and all of this stuff. And then you follow the math. And it turns out by doing all of this, and I know this is kind of not believable at this point because I'm like not going into any detail. But this is actually where the numbers come from. So people have understood this very, very, very well. Extremely well. And the point is, it starts with Schrodinger's equation. It tells you what psi is going to be. And in certain cases, you can actually solve it explicitly by following the math. And the math seems complicated, but I think it's just like very tedious arithmetic with imaginary numbers, which sounds like great. It's not even real math. This is great. But it actually is. So I think, where do the numbers come from that you can get this nice picture of superposition, this nice sine curve? Well, just think, it comes from the quantum analog of Newton's laws of motion. So if you believe that you can predict what a classical object is going to be doing in a certain amount of time, given some equations, thanks to Newton, if you can imagine there's like a quantum analog of that, then that's kind of how, so people can feel like it's not magic or something unreachable. There is a path to get there. And it boils all down, to answer your question originally, to Schrodinger's equation.
Gotcha. And then that becomes the applied piece for executing gates. So like to bring it all the way back to this DiVincenzo's criteria.
Yes, thank you. Yeah, exactly. So a gate is like you can say, I want my initialized qubit. Initialized, we talked about that last time. So it's in the ground state. But I want to actually put it in a superposition of, 50% ground and 50% excited. Like I want it to be like the quantum version of a coin toss, 50-50. So a gate is, you go back to the picture of superposition, you have your laser and you have to make sure that the wavelength of the laser is appropriate. So that's factored in too. And you say, how long should I shine my laser for? So there's a certain amount of time. And I think for for like some mathematical reasons, you may need to do like a sequence of pulses to get it. But the point is that you know how to do that. Like the mathematics says, oh yeah, take this particular laser, shine it for this, amount of time and have it incident at this particular angle. And once you know all of that, what happens is that at the end of the day, after that laser pulse or that sequence of laser pulses, your ion is now in a superposition of ground and excited. It's no longer in the initialized state. It's in a superposition of the initialized plus the next state up, the excited state. And that whole operation, that laser pulse or that sequence of laser pulses, that is called a quantum gate. Now, mathematically, we represent them as matrices, like that Excel spreadsheet thing. So sometimes if you're reading like a math book, you'll see people refer to quantum gates and then they'll call it a matrix or a unitary matrix. They're just talking about the mathematical representation of these laser pulses or sequence of laser pulses. And the fact that you're doing it on one individual ion, that's why it's called a 1 qubit gate, because you're shining your laser on one ion.
Okay.
So
that's
it.
Okay.
That's it.
Yeah, no big deal. And then, I think from talking about like how long it actually takes to do that, for these single qubit gates for a trapped ion quantum computer, I think I was reading that it's on the order of milliseconds in order to be able to go through all those laser pulses, and the gaps between the pulses and the gaps between different gates. That it kind of adds up into the millisecond range. I think that's what I was reading.
Yeah.
Is that?
I think I read that too. That sounds fast to me.
Yeah, it's pretty fast.
But
and we'll talk more.
I don't know.
Yeah, we'll talk more about DiVincenzo's third criteria, which talks about like the decoherence, the long decoherence times, which means basically how long can you keep, in this case, the ion trapped in a state that's coherent, meaning that it's doing what you want it to do and isn't being like interfered with by outside forces or sort of drifting back to its ground state or something near that. There's a certain amount of time that you have after initialization before you have to kind of initialize again. And that time is pretty short for trapped ions, like for calcium ions, but it's long enough, much longer than milliseconds. And that's really, I think, the differential that you have to look at. How long does it take to actually do the gates, or to execute the gates, which you need to do in order to do a computation? And how many of those can you do before you start to lose that coherence of your qubit and have to kind of start over again? So milliseconds can seem really fast, but they can also seem really slow depending on what your coherence times actually are. And I know we'll talk about that in a future conversation. As we wrap up, I know we always like to kind of have like a superconducting quantum computer corner where we talk a little bit about superconducting quantum computers in the context of the conversation that we just had, because superconducting quantum computers are pretty popular out there. So any sort of differences or similarities from the conversation that we just had, I think the math still works out. Like the math is universal, sort of for figuring these things out. As far as I know, does that align with your thinking of things? Like most of the formulas and equations you were talking about, it's kind of agnostic to the the realization of the qubit.
Yeah, Schrodinger's equation is where it's at for sure.
Okay, so that's good. I think there's a couple of pieces that are a little bit different here that I can just mention quickly. One, we've been talking a lot about lasers when we were trying to manipulate the states or going through gates. We talk about like turning lasers on and off very, very quickly. With a superconducting quantum computer, it's a different kind of electromagnetic energy. It's microwaves. So microwaves have less energy than visible light, but it's all on the electromagnetic spectrum. So you can even talk about microwaves in terms of photons. A microwave photon, for example. So the control is very similar in a superconducting quantum computer as compared to a trapped ion quantum computer, but instead of shooting laser light, you're shooting microwaves. So you have some of the same challenges there of needing really, really specific timing with your microwaves and lots of control there. And every qubit needs lots of microwave control to be able to control that qubit very precisely. So that's one similarity, but also different. So it's still electromagnetic energy, but it's a microwave instead of a photon. The other thing we were talking about with timing, with how long it takes these gates to be executed in a trapped ion quantum computer, and in a superconducting quantum computer, it's much faster. So it's more on the nanosecond time scale versus the millisecond time scale.
Yeah.
And as far as I know, gate times in superconducting quantum computers are some of the fastest, if not the fastest known gate times in quantum computers right now. So that's another sort of advantage that that superconducting quantum computers can have. There's lots of advantages and disadvantages of all the systems, and that's one thing that superconducting quantum computers have going for it, are really, really fast gate times. So you can execute more of them before your superconducting qubit decoheres.
Okay, nice, fantastic. So we have chatted about part of DiVincenzo's criterion number 4. We spent basically the whole episode talking about 1 qubit gates for trapped ions and a little bit for superconducting qubits. And we have saved now a discussion on 2 qubit gates that's affecting 2 qubits at a time for next time, because this is actually where entanglement comes in. And I think, Adam, just like today's episode, I hope, demystified this concept of superposition, I think next time we can do the same for entanglement, which has a lot of spookiness surrounded by it. But the more I read, the pleasantly surprised how actually concrete and understandable it is, at least from a math and like engineering perspective. So maybe we can chat about that next time.
Yeah, I'm definitely looking forward to it. You kind of took the words out of my mouth, which was, I'm hoping you can do the same thing for me for entanglement that you just did for superposition. So I'm really looking forward to our next chat.
Yeah, okay. I hope so too. We'll see how it goes.
Okay, great.
Okay, until next time.
Until then, thanks.